What does it mean for a function to not be differentiable at a point? That is, for the derivative at a particular point not to be defined. This is an important idea that we need to understand to help us do a little piece of this section. Let's look at 3 examples. Now we're assuming that our function is continuous. Our graph to start with doesn't have any breaks, okay? We're making that assumption. Notice all 4 graphs on this page are continuous. There are no breaks. First example, f of x equals square root equal absolute value of x. Well, we know that we can define absolute value of x in 2 pieces, in 2 linear pieces. Absolute value of x is just x if x is greater than or equal to 0. Absolute value of 7 is 7, right? Absolute value of x is negative x if x is less than 0. By the negative x, we mean the opposite of x. So absolute value of negative 7 is the negative of negative 7, the opposite of negative 7, which is positive 7. Okay? So if we look at the graph, here's y equal x, and here's y equal negative x. What's the derivative? What's f prime of x? Well, it's 1. The derivative of x with respect to x is just 1. If x is greater than 0, I'm not putting equal to here. We'll analyze 0 here in a minute. But certainly if x is greater than 0 on this piece, the graph itself is linear. So the tangent line is the graph itself, and the slope of the tangent line is 1. How about this piece? The slope of the tangent line is negative 1. The derivative of negative x with respect to x is negative 1. Now how about at 0? What's the derivative? Well, there just is no tangent line here at this point 0, 0, because we've talked about this a few times in class. If you zoom in on this point 0, 0, the graph will always have a sharp corner, right? It'll never look like a straight line. It'll just never look linear at this point if you zoom in. That's because the secant lines that go through 0 and points to the right of 0 have a slope of 1. And the secant lines to the left of this point have a slope of negative 1. The slope of a tangent line is the limit of the slopes of the secant lines, but the right-hand limit of the slopes of the secant lines is 1. The left-hand limit of the slopes of the secant lines is negative 1. So the right-hand limit of the slopes of the secant lines doesn't equal the left-hand limit. 1 doesn't equal negative 1. So the derivative at 0, f prime of 0, does not exist. How can I tell just by looking at this graph? There's a sharp corner there. If a graph has a sharp corner, derivative doesn't exist there. Differentiable means, in a graphical sense, smooth. Okay? F of x equal x to the 2/3 is another example. Well, let's take the derivative. F prime of x is 2/3 x to the negative 1/3, which is 2/3 x to the 1/3. Notice that f prime of 0 does not exist, is undefined here, because you can't divide by 0. Okay? The derivative is 2/3 x to the 1/3. What makes this derivative undefined? If x is 0, it's undefined. Notice what happens to the graph at this point where x is 0. Again, there's a corner there. Sometimes that's called a cusp, but it's certainly a corner. It's not It's not a square corner, okay? The graph coming into this point is curved, but it's still a corner. It's a sharp corner. In other words, if I zoomed in here at this point 0, 0, if I zoomed in, the graph would always have that corner point, right? It would never look linear. Okay, how about f of x equal x to the 1/3? Well, f prime of x is 1/3 x to the negative 2/3. Again, f prime of 0 does not exist because this expression has division by 0. It's undefined if x is 0. Well, what happens to the graph in this case? There's a vertical tangent. Here's an example of a vertical tangent. Up here we had sharp corners. The graph still passes the vertical line test, but it comes awfully close to not doing it. The graph flattens out vertically right here at this point. Again, I can't tell which of these is going to happen just from my equation. That's an important thing to know. And I'm creating all these examples where just trying to create examples where the first derivative is undefined. I'm picking examples where it's undefined at the point 0, 0. But I could pick examples where the equation was a little more complicated, where the first derivative was undefined some other point. I'm just using 0, 0 for simplicity and consistency. Now let's compare that with f of x equal x squared. We know f prime of x is 2x. Well, 2x is defined everywhere. You put in a real number for x, you get a real number. The derivative of f of x equal x squared exists everywhere. There is a tangent line at every point of this graph. Particularly, there's one at 0, 0, right? It's a horizontal tangent line. Notice if I zoomed in on this graph at 0, 0, into a very small window, this graph would look horizontal. If I put in 0 into the derivative, I get 0. Slope of a horizontal line is 0.